Good afternoon, ladies and gentlemen, and welcome to yet another exciting SIMM webinar. I'm Buhle Kagalashe, a Chief Engineer in the Pyrometallurgy Division at Mintech, and I will be chairing this webinar. Our speaker for today is Dr. Balomenos, all the way from Greece. Dr. Balomenos studied mining and metallurgical engineering at the National Technical University of Athens in Greece. And he received his PhD degree in thermodynamics in the same school in 2006. Since 2008, he has been working in the lab of metallurgy as a postdoc researcher, focusing on sustainable process development, CO2 mitigation strategies, exergy analysis, and resource utilization efficiency. He was involved in the research management of a few European projects, including the NXL, the URE, and is involved in the ongoing EU projects, including SCALE, Surreal, Removal, BioRecover, and LSIC projects. He has more than 40 research publications in journals and in conference proceedings with more than 500 citations, and he has an H index of 13. Dr. Balomenos has presented at a number of international conferences, including giving keynote addresses. And since 2015, he has been working with Metallurgical SA, Metallurgy Business Unit at Aluminium of Greece, where he focuses on promoting sustainable solutions for the valorization of bauxite residue. From this impressive CV, ladies and gentlemen, we are in capable hands. So back to today's topic. And it's a continuation on the theme of sustainable in metallurgy. Dr. Balomenos will be taking us through his talk entitled Exergy in Metallurgy. Exergy is a tool for evaluating sustainability in metallurgical operations. And for your information, ladies and gentlemen, the presentation will be circulated to the participants. And please kindly ask your questions on the chat under Q&A. And over to you, Dr. Balomenos, and looking forward to a highly educational and exciting presentation.
Thank you, Buhle. Thank you for this very kind introduction. I can start now, I think, my video feed. Yes. Thank you. Good morning, everyone, or good evening, depending on your time zone. I will share now my presentation. So I hope everybody is seeing my screen. Buhle, is it coming on?
Yes, it's on now.
Okay. So today the lecture will be on, as Buhle said, on Exergy. Exergy as a tool of sustainability in metallurgy. It's a big subject. There are quite a few slides. I will try to be fast through them, as this is meant as an introduction. Hopefully that people attending this webinar will be interested further and start looking deeper into Exergy, which I think is a very interesting tool for metallurgy. So starting from the basic definition of Exergy, it's part of the energy that cannot be converted, that can convert other forms of energy. I will explain this more in the presentation. So why Exergy metallurgy? This is of the primary alumina and aluminum production. This is what we call a mass and energy diagram, and that's exactly what is we have to instate diagram, compare mass and energy, and this is a problem when you want to see how environmentally sustainable it is, because we don't compare energy. We have the bioprocess energy inputs, which is fuel. We have the production process, electricity, which may be used again from renewable resources like coal burning, and therefore you cannot really judge what is the impact of this process. So we go to thermodynamics. Some basic definitions I will go over. thermodynamics defines a system which has some intensive properties like pressure, temperature, and chemical potential. It has some intensive properties like internal energy, entropy, volume, and mole numbers of moles. And this system is isolated from the environment. It has no interaction with the environment. It will isolate. If it's a closed system, it can exchange energy, but not matter, with the environment. And in the open system, it can exchange both energy and matter. So in these types of systems, when you have differences in intensive properties, you will lead to have changes in extensive properties. This is a very simple idea. Just imagine a balloon that has a different pressure from the environment, and this difference of pressures will lead the balloon to inflate or deflate. So these intensive properties, the difference of the intensive properties, are thermodynamic forces that lead to thermodynamic fluxes, which lead eventually to thermodynamic equilibrium, where the balloon has now the same pressure with the environment. And we can put some mathematics on these concepts, and you can see that forces, when they are multiplied by the corresponding fluxes, actually give us the rate of entropy production in the system. So as we transcend to thermodynamic equilibrium, entropy is being generated. You most likely, everybody knows the second thermodynamic law that says that entropy in an isolated system must always increase in every non-reversible process. But what does that really mean? What does entropy stand for? If you take a textbook, you will see that it's related with the numbers of states, microscopic quantum states, that the system exists, which the equivalent microscopic states. So the molecules inside the blue balloon have many configurations, but no matter the configuration, they end up having the same temperatures, pressures, potential, and so on. So entropy is defined by this formula here, and if we show that all the states have the same ability to materialize, then this is further simplified to this formula, and we can now see that we will maximize the entropy of the system when we need the maximum amount of information. The system in this case will be in complete randomness or in fully disorder. So the second thermodynamic law states that all isolated systems will tend to maximize the number of macroscopically equivalent states, meaning that we will increase the information needed to describe the system. The system will be configured in such a way that it can exist in the most possible ways. When we have just one possible state of the system, then we have the absolute order, meaning that we need the minimum information for this description, and it goes to zero. In fact, the capacity to store information within a system is a measure of its order and structure. So this goes a bit towards another branch of Exergy, which relates to information capacity, which is actually measured in bits. So entropy can be related to information. This is not so important for what we want to see here. What is important is this attribute, which is called entropy, which is the distance between the entropy versus the entropy of the system equilibrium. So we will see this in the next slides. Final thing that we need to clarify Exergy before Exergy is that entropy production must be defined internal and external production. So we have something happening within system A. This causes a change in entropy, but since the system is isolated, you have no change in the entropy of the environment. So according to the second thermodynamic law, obviously the change in the system has to be positive. In the old system, imagine that something happens in the system and there's a change of entropy. One part of it stays within the system and the other part of it is exchanged with the environment. So that's internal and external changes of entropy. Obviously, the environment undergoes the opposite of the external entropy change. And then if we go again for the total change in entropy between system and environment, we see that what needs to be positive is the internal change of entropy in the system. This means that we can have an entropy flux from the system to the environment that is negative, and in fact it could be even greater than the internal change in the system. Then the system will decrease its entropy. This is what happens when you put something warm in your refrigerator. The entropy of the refrigerator will decrease. However, the total entropy of the system and the environment will never decrease. In total, the entropy of environment and system will always increase. So, very fast recap, because the thermodynamics is always a bit complicated subject. When we have difference in intensive properties between system and environment, we have thermodynamic forces. These forces cause fluxes, and these fluxes will lead us to thermodynamic equilibrium, generating entropy along the way. According to the second thermodynamic law, all systems will tend naturally to achieve thermodynamic equilibrium, and the total entropy of the system and the environment will always increase. And entropy is somehow related to the information needed to describe the system. These are the basic things you should keep in mind for the next slides. So, despite this natural tendency for equilibrium, our environment, our universe is far from equilibrium. So we have a sun that has almost 6,000 degrees in its surface. At the same time, Earth's surface is at 15 degrees. The space surrounding us and the sun is at 2.7 Kelvin, and humans have a temperature of 36 degrees Celsius. Molecular weight between organic and inorganic matter differs significantly. Density between the upper parts of the crust and the lower and the core of the Earth is hugely different. So we have a lot of systems around us that are far from the state of thermodynamic equilibrium with their environment. These systems are called energy dissipative structures, which means they have the ability to remain far from equilibrium by the constant consumption of external energy and matter. This is, for example, how our bodies are kept warm and we don't come into thermodynamic equilibrium with the environment. We keep eating, and therefore we keep breathing. Yeah. But of course, this statement is false, because energy and matter is preserved in all processes. Therefore, we are not consuming energy and matter. We are constantly consuming quality of external energy and matter. So what's happening is that we are degrading the quality of energy and matter that we are consuming. Let's imagine a system, let's say planet Earth or an internal combustion engine of your car. These systems take as input energy and matter. So it could be solar radiation coming, shortwave electromagnetic radiation, or it could be gas in the car. And they are able to keep going, right? But at the same time, they are rejecting energy and matter in terms of thermal radiation or off gases, and so on. So what is happening is that we're giving energy and matter with high quality, and we are rejecting energy and matter with low quality. The measure of this quality is called exergy, and exergy is measured in energy units. So whenever we have an exergy flux, This can create and sustain the structures away from thermodynamic equilibrium, and these are the dissipative structures, like our planet. Or it can lead to equilibrium when the flux is exhausted and we have a decaying structure. But always exergy is being destroyed. We have higher exergy coming in, lower exergy coming out. So how do we define exergy? That was the concept, but how do we define it? The system interacts with the environment. It can be exerting a work, and then you have some very simple definitions between the system and the environment. I will not give too much time to the math here, but by doing some simple calculations, you derive that this parenthesis here can be called the change in exergy, right? And so exergy is the difference of the internal energy of the system with the intensive properties of the environment times the extensive properties of the system. So it's the temperature of the system, of the environment, times the entropy of the system, the pressure of the environment times the volume of the system, and so on. And the work that we can exert from the system is, from this definition, is the exergy minus the temperature of the system times the total exergy entropy production during this work production. And since the entropy change will always be positive or non-negative, then the work can only be less or equal to exergy. Therefore, exergy is the maximum attainable work in any system in a given environment, right? The rest of the energy of the system, of the internal energy, is called anergy. It is what we can never use. So the energy of a system in relation to the environment, we have defined it with this formula. Now, it's easy if we substitute the internal energy to see the exergy even clearer as the difference between the intensive properties between environment and system. So exergy measures the contrast of the system to the environment. As we move towards thermodynamic equilibrium, where the intensive properties will all be the same, we have a change of entropy, which has to be greater than 0, and we have an exergy present in the initial state, but in the end, when we get to thermodynamic equilibrium, we have 0 exergy. During this transition, we assume that there was no work produced. Therefore, the total change of entropy is related directly to the change of exergy. And again, here we can find the term of negentropy, which is easier to realize as the total entropy of the system now versus the total entropy of the system when it reaches equilibrium. How much energy, how much entropy has to be generated to get to equilibrium. So exergy and negentropy measure the quality or the divergence or the excess of information of a system in relation to its environment. So in many subcases, actually, exergy has already been defined in thermodynamics. What do I mean by this? So if we get a system where we have no change of number of moles, we have no change, we have pressure the same as the environment, and pressure the same as the environment, and practically change in exergy equals the change of the free energy of Gibbs. Similarly, if we take a system where we have no change in volume and the temperature is equal to the temperature of and exergy is related to the free energy by Helmholtz, and similarly to enthalpy in terms of when you have no change in entropy. So practically, energy is the quantity which thermodynamics initially seeks to define. And when I'm saying initially, I mean back in the days of Carnot, what was thermodynamics was looking to define what is the maximum work or the reversible work or the ideal work. And then we got more and more terms like free energy, available energy, Exergy, and so on. So to give one final visual idea on Exergy, it's all a contrast. And here we can use aids. Contrast, philosophically, will create tension, and tension is the prerequisite for conflict or for work or for even existence of time. But if you take away the contrast, and we can do this very easily by sliding the bar in any picture in our laptop that says contrast all the way to 0, you get this effect, right? Now, all these paintings are right, and they have, if we're discussing about Exergy, now we are at the state of thermodynamic equilibrium. Exergy is 0, and we can get no work or money for these paintings. This is called the dead state. It's where the intensive properties of the system are now defined by the environment. When your temperature is the same as the temperature of Earth, you're usually dead. Dissipative structures consume Exergy to maintain these contrasts to the environment so they can live, so they can produce work. In metallurgy, we have reactors that we need to spend a lot of Exergy to maintain at conditions that are far from the environment, in strong contrast to the environment, in order to produce our chemical work, so to produce molten metals, for example. So Exergy is a concept that allows us to visualize process efficiency in reference to the environment. And this is how it becomes relevant to ecology. When we want to understand better what's the difference between energy and Exergy, okay, first, they're both coming from Greek words. Energy is the work within, Exergy is the work outside. Energy is motion or potential for motion, while Exergy is work or potential for work. And if you want to be simple about it, work can be more organized motion. Energy is always preserved, while Exergy is only preserved in reversible theoretical processes. Energy is always greater than 0. Exergy becomes 0 at thermodynamic equilibrium. Energy is independent of the environment, while Exergy is defined by the environment. Energy is quantitative, so you know how much energy you have. Exergy is kind of qualitative because it's always relating to the environment. And the various forms of energy have different degrees of quality, or let's say, of how much of it can be transformed into another form of energy under the process. So we have potential or kinetic or electric or magnetic energy in my system. In ideal conditions, so without any heat losses and traction and so on, you can change from one energy to another without losing any work. But when you get to the more disordered forms of energies, like nuclear, like solar radiation, like chemical, like steam, like low-level thermal radiation or thermal radiation of our planet, the quality of Exergy, the work that you can attain, drops significantly. These numbers are just indicative, of course. So non-organized forms of energy cannot be fully transformed to work, even under ideal conditions. And this is where we go back to Carnot, and you can see that the maximum work attainable in this cycle is, of course, equal to Exergy. And whenever we have heat-related processes in transformation of energy, the maximum work is always defined by the temperature difference between the system and the low reservoir or the environment. So let's see one final example of how Exergy was firstly used in mechanical engineering applications. This is a simple schematic of electric. I'm producing energy by boiling water, producing steam. The steam rotates turbine, you produce electricity, then the steam is cleansed and re-enters the boiler system. Conversion of chemical energy to thermal energy by burning some sort of fossil, then conversion of thermal energy to kinetic energy by generating steam, conversion of kinetic energy to electrical energy, and some heat water. If you use energy flow, you see that major energy the base heat are not before. But if you see energy flow for the system, you will see that the major exergy loss happens at number 1. This is exactly where the exergy balance can provide new insight to a process, because the energy balance does not provide us any information on what's the potential of the energy we're discussing to produce work, right? So by looking at the exergy system, we can now see that if we want to optimize our power plant, we should not invest more in waste heat recovery at the condenser where the steam is at 60 or less degrees, but we should spend more time to optimize the transfer between 1 and 2. And this has actually taken place. Supercritical boilers have improved the overall exergy that we can pump into the steam, and this is what is used today. And if you want to go a step further, then maybe you can say that, okay, I don't want to be burning something to boil water. It's better that I convert directly the chemical energy of my fuel to electrical energy using a solid oxide fuel cell, and so on. So we go now to the metallurgical part, which is the chemical exergy. The chemical exergy is this final component into this equation. You can see here. So it's the difference between the chemical potential of the system and the chemical potential of its constituent in the system versus the chemical potential of this same compound in the environment. You end up with this formula where Ci is the concentration in the system and Ci0 is the concentration of the same element in the environment. And we can then take this, simplify this a bit, and define the standard chemical exergy of the I component. So the chemical exergy of a material is the exergy needed to synthesize the material from the environment under reversible processes. Similarly to what we saw before with energies, we can again have in our minds that we have materials that are high in exergy, that are well structured, or are super pure, and we have the highest degree of exergy, and they need a lot of exergy to be created, or they can release a lot of exergy upon their destruction. But as our products become less and less pure, their exergy diminishes. So a rich mineral concentrate might have significant exergy. A poor ore body has less. A metal that is dissolved in water and soil has zero exergy because it's practically in equilibrium with the environment. We will more. Let's show a reaction. The elements that this contains and thermodynamics has defined the formation of this reaction by its formula. And thermodynamics says that the chemical potential of its element so we say that elements cannot be created or destroyed in chemical reaction, therefore we define all the chemical potentials of the elements as zero. This allows us to be able to calculate the free energy change or reaction through the standard Gibbs free energy information, which is determined experimentally, and this allows us for most of the thermodynamic modeling So let's try to see how we can do this using Exergy. The same idea here, but instead of delta G, we go with delta B. And this time, we say that the elements are not in equilibrium with the environment, because in the environment, they are not found as pure elements, and therefore their standard Exergy cannot be 0. But if we go under constant temperature and pressure, as we said before, the delta G can be equal to delta B, and therefore we can have this formula by which we can define the standard chemical Exergy of a compound in relations to the Gibbs free energy of formation and the reference elemental Exergy of its components. So how will we define? What we need to define now is this green reference element Exergy. Reference states for the chemical elements in their environments, we will accept their most common compounds in nature. So when we're discussing about the reference elemental Exergy of hydrogen, we will select water. So we frame chemical compounds in nature. So we define that the element in the environment has a reference state which corresponds to its most common compound, and a compound has an Exergy of 0. So let's see an example. Oxygen. The reference state is obviously oxygen 2 in the atmosphere. The concentration in the atmosphere is 20.4%. Therefore, the reference chemical Exergy for this substance, for oxygen 2, can be easily found to be 3.97 kilojoules per mole. If I go to iron now, the reference state would be, say, hematite in the earth crust. We can go and use some average concentration and find that in the lithosphere, the hematite is found in this concentration, and then again use the same formula to calculate the reference chemical Exergy of hematite. Knowing hematite and the formation of hematite, easily find Exergy of oxygen, we can derive the chemical Exergy of iron. And you can see this chemical Exergy is 377 kilojoules per mole, and this is the Exergy required if we want to extract metallic iron from hematite in the lithosphere under reversible processing. Similarly, we can keep going and find the chemical Exergy of magnetite, bauxite, so what we see here, the Exergy for the iron oxide and metallic iron, and we can see that the oxidation state reduces. So as we see, the Exergy gives us a very clear picture of the quality of matter in our environment, which is highly oxidative. So it quantifies the matter around us in a more logical way, whereas the free energy formation, which was our usual reference in classic thermodynamics, has little relevance. You can see that the numbers are really arbitrary. Plus, we now know that the production of metallic iron from pure hematite requires so much energy under reversible processing, so 6,000 kilojoules per kilogram, and we can directly relate this to how much the modern day production of iron consumes energy. Of course, it's between reversible processing course, if you now all this you find as reference books, you don't need to start doing all this work from the beginning. You can go directly to this type of charts and find the elemental energy of its element. So, the higher the chemical exergy, the more rare is this element in the environment, and the more valuable it is as a resource. We can imagine the process happening in nature on the left. So we have sunlight coming into our planet. We have various reactions taking place in the biosphere and in the atmosphere and in the hydrosphere, and all through this these processings, there are some waste that are being created. They are decomposed and they go into the lithosphere or the hydrosphere. Similarly, in the environment, in our social sphere, in our what humans do to the planet, we extract usually minerals and deposits and resources from the lithosphere and the hydrosphere, and we go into production, consumption, and the waste is returned back into these spheres. So when we see these charts, if we change them into an exergy chart, we can have this picture. So we have a huge exergy flow inside the planet, going to our little beaker here, which is the planet Earth. This exergy flow creates various substances found in mineral deposits, in forests, and so on, in farms. And our society is taking out exergy flows to be used for various productive properties. Therefore, it's clear that this process is only sustainable as long as we keep, as long as we don't overdraw exergy faster than exergy is replenished. This, of course, is difficult to do in a planetary scale, but when we look into industrial process, then we can see that this is controlled basically by two boundary conditions. One is economy and the other is thermodynamics. And Exergy has a way of combining them both. Because now we have a value that gives us for each product and byproduct we produce, we now have a value for it. That's comparable and defined. So if we want to do sustainable development, we need to satisfy the needs of the present without compromising the ability to satisfy the needs of the future. If we look at the life cycle of any operation, let's say that this is a power plant, we will spend Exergy when we build the plant, then we will spend Exergy as we use lignite, petrol, or natural gas, or whatever fuel produce electrical energy, which is the positive gain for this operation. And someday the plant will close, and then we will spend some more Exergy in order to clean up the site. So this is a non-sustainable, obviously, a picture. If we are using renewable resources in our accounting, then the energy coming in is considered free because this electricity can be renewed. And you can see that the same graph gives us a sense of at what time we will have produced enough Exergy in order to have a bonus of Exergy through the entire life cycle. So this is how sustainable development can take place with exergetic life cycle analysis. You need to have operation where the total Exergy spent over the lifetime of the unit or the process will be equal or lower to the Exergy produced from this plant. And reaching the Exergy balance now. The Exergy balance provides us information on optimizing the thermodynamic processes. The Exergy utilization coefficient of the process quantifies its inherent imperfection. It can be used to directly compare two different processes with the same product. It's very simple. It's at the denominator, we have the exergy of the useful product versus the exergy we spent in the process. This will always be smaller than 1 because exergy is always being destroyed. Also, please note, we're only putting the product, not the byproducts. So therefore, this is a clear indication of how useful our exergy that we spent was. The exergy of one product or its byproduct can also be used as an approximation of its value on market. High exergy means that this is a rare chemical compound in the plant. It means that it stands very far from the environment. This can also be a bad thing. So, something toxic will also have a high exergy. And finally, the total exergy consumption of non-renewable resources used in the production is the direct measure of its environmental cost. And this is, again, defined in energy units. So we put exergy into our plant, we take exergy out of the plant, there is always a loss, which is tied to irreversible processing, and this loss is the direct measure of our environmental cost. So if we want for the same product to be more sustainable, we need to minimize the exergetic losses. Today, we are actually doing some sort of valuing of products and services, and we're using CO2 as the base for this measurement. CO2 is an atmospheric pollutant, obviously, and a byproduct of this process, but practically, it is a measure of non-renewable fossil fuel consumption. So we come back to the alumina and aluminum production. We have this flow sheet, and now we will try to change this into an exergy balance. So we first identify the chemical elements that are involved in all the processes. It's the small list. And we take directly the exergy of each element from a table found in literature. Then we define the standard species involved in all our flow sheets, and we calculate the chemical exergy using a formula on the left based on the chemical exergy of the M elements. It's a very straightforward process. Of course, in these calculations, we will always need the free energy information for each of the species, and that we can take from a database. But also in our process, we will come up with minerals or complex byproducts like bauxite or red mud. How do we define the exergy in these cases? Well, then we go for the exergy of a mixture, which is defined by simply using the standard thermodynamic formulas for mixtures. In this case, we will assume that all our mixtures are ideal, and therefore we will use the formula you see above. And simply by knowing the composition of our ore and defining how many grams we have of this species, we can calculate the exergy or as 0.14 megajoules per kilogram of exergy. The red mud bauxite residue coming out of the Bayer process as a residue, as a waste, contains mainly iron, titanium, complex, and again, we can assign energy, find that in fact the a bit higher than the bauxite, and that's fairly reasonable because bauxite ore is uses very common compounds found in the environment, whereas the bauxite residue, the red mud, has much more soda and calcium inside of it, making it a bit higher in exergy value. So then we go back to the mass balance, mass and energy balance. We now have large flows like bauxite, we just calculate the exergy per kilogram. Therefore, just by multiplying the mass to the exergy, you have the exergy component for each of these inputs. You have utilities coming in. Let's say it's diesel fuel. Here, the chemical exergy of any fuel can be easily found by its higher heating value. Therefore, we calculate the utilities coming into the operation. We have a product, trihydrated alumina gibbsite. Again, we tie that to an exergy, and we have some waste streams or byproducts, which again we calculate here. So we can do the sum of this compound, of these streams, and end up with this exergy figure, where you see that the input in terms of materials has an exergy total of 1.16 megajoules. We add 28 megajoules in fuel utilities. We take out 0.81 megajoules as a product, the aluminum product. We take, we lose exergy in our waste products, which is by CO2 and bauxite residue, and the rest, what is lost, is waste heat. This is the exergy that is destroyed in the process. Now, if I do the exergy coefficient, is very low because it's basically 0.81 divided by the sum of the utilities and the input, so something like 30. And on the right, you see further on the Hall-Herle process for producing aluminum. Do with this type of modeling and this type of exergy calculations is that you can imagine how your system will be better if you take, for example, a byproduct like red mud and try to utilize it, for example, in an EF process. In this case, you see that the total exergy of the entire new system is doubled from what was like 3%, 4%, it's now going to 8%. So this gives you a direct idea of whether taking bauxite residue and converting it into pig iron and mineral wool is a good idea in terms of sustainability. Going to the electrolytic part of the process, here we do the exergy balance, taking two scenarios. The one scenario is we have power produced from hydroelectric plants, so kind of renewable, and then we take the worst case scenario of powered our process from coal burning plants. As you can see at the bottom line, the change in the exergy efficiency of the two processes is very big. So when we are burning coal to produce electricity for our aluminium production, we have close to 16%, but when we get hydroelectric, so we are not wasting a lot of resources to produce electricity, our exergy efficiency is close to 40%. And again, the same, seeing how this process can be better, we can compare it directly to the theoretical carbothermic reduction at an electric arc furnace, where using again coal-produced electricity, we will end up with a bit higher exergetic efficiency utilization factor, as you can see in this calculation. This is of course theoretical, as this process has not been achieved to this degree. We assume that we get the same amounts of outputs in both cases. So that is somewhere here is the end of my lecture, and I can open the floor to any questions from the audience.
Many thanks, Dr. Balomenos, for that inspiring presentation. We only had a glitch with the sound. The sound quality was not so good, and the members were also struggling a bit with that. So, but except for that, the presentation, I was glued to my screen so that I could hear as much as you, as much content as you presented. So at this point, there are no questions as yet from the attendees. Okay, there's a first one. So there's a question from Ivan. Are there any benchmark values for the Exergy utilization coefficient? For example, if the efficiency is below 20%, then the process is inefficient, or it can be used only to compare between two options.
Interesting. No, there are not.
Okay. Okay, so there's a question from my side. So I see then you did mention that there is LCA with this exegetic analysis. So do you normally do this? Do you collaborate a lot with the guys that work with the conventional LCAs or not? Is there any value in doing that?
Well, I have been to conferences where there's a huge debate between those that are fans of exergetic life cycle analysis and those that are doing the conventional life cycle analysis. So sometimes there's an academic dispute between these two groups. But I think you need to do both, and they give you different type of information. From my side, Exergy is much more straightforward and thermodynamic than the conventional life cycle analysis, where you have, in the end, you get some figures that speak about, CO2 or eutrophication factor, and you get numbers that are very difficult to comprehend. They're just numbers on a scale. So that's the big difference. Of course, with databases created for LCA currently, you can. It's much easier to do a global study than with the available information on the exergetic life cycle analysis. If we build more on exergetic life cycle analysis, you will be able to get more global results. There are programs like HSC that do have an Exergy component inside. Therefore, you can actually do calculations not by hand as I showed here, but you can do them through a computer.
Okay, thanks for that comprehensive answer, Dr. Balomenos. We have one other question. Thanks for the presentation. Have you done any Exergy calculation for aluminium production, including the intermediate production of aluminium carbides, and reacting this with aluminium oxide again, or any other carbothermic aluminium production that has been achieved? Dr. Balomenos?
Can you hear me?
We can hear you now.
Okay. Yeah, what I presented here was a very simple, straightforward, let's say, envelope approach. We just looked at what's coming in, what's going out, and we didn't look at the intermediate phases or the complexity inside the carbothermic reduction. Exactly because the process is not so well known or so well documented, but we kept the same level of detail as in the primary aluminum case. So it was just inputs and outputs, a very simple approach. If you want to get really insight in the process, then you can do this envelope approach, and then you can start looking at each one of the reactions, zooming in if you want, and understanding where you're losing Exergy or where your system is not really working well. And that will be much more effective in understanding what is happening and what you can improve. I can give another example for the Bayer process. This very low Exergy efficiency is, for example, we're not taking into account the precipitation effect and the Exergy spent in crystal growth. These are much more difficult to simulate and to understand. This is you always need to keep in mind that the Exergy balance I just showed you is things coming into the plant at the gate at 25 degrees and exiting the plant as products or byproducts again at 25 degrees. We did not discuss their morphology or their temperature or other properties.
Okay, thanks for that. So another very relevant question, again, is a thank you from Jack. I found this fascinating and useful. He studied pyrometallurgy in the 80s, and Exergy was never considered in any of the processing steps. So has this changed? So are the more recent graduates qualified with this knowledge?
Yes, I certainly hope so. I mean, it's gradually, I've seen it the last 10 years and 15 years that I have been looking into it, that it's gaining more and more ground in textbooks. It's widely used in mechanical engineering and sometimes in chemical engineering, mainly for enthalpy calculations. But there is increasing literature on how it can be used in metallurgy. So I don't know if there is a specific course in metallurgy training on Exergy, not in my school anyways yet, but I think it's gaining ground.
Okay, thanks, Dr. Balomenos. Okay, so that concludes the questions from the side. So what will happen then, the presentation will be circulated, but again, we struggled with the sound quality. So we'll discuss further on how to best get the content through to the attendees.
Yes.
Okay, thanks a lot. There are no more questions, and that concludes this webinar.
Okay, thank you very much for this opportunity.
Okay, cheers, Dr. Balomenos, and cheers to the attendees.
Goodbye.